Entropy and intermolecular forces, effects on solution formation. Now let's talk about how solutions form. There are two learning outcomes listed here, but these are very reliant on the materials that we have covered before. So be sure that you remember what entropy is, what intermolecular forces are, and their relative strengths. Using that, we will cover how entropy is related to solutions and identify the effects of intermolecular forces on solution formation. Entropy is a measure of energy randomization. We often call this the measure of disorder. If no other forces were present, entropy would drive solutions to mix evenly. This force is what creates solutions, and if there was nothing else involved, would be why everything would turn into a solution. However, as we know, not everything in life is a homogeneous solution, and that's because other forces come into play. Sometimes molecules are held together more strongly than the forces of entropy that wants to pull them apart. This is where the strengths of intermolecular forces come into play. Intermolecular forces can stop solutions from forming. A typical high school level chemistry phrase that is still quite useful to us is that like dissolves like, which is to say that polar species dissolve other polar species, while nonpolar species dissolve other nonpolar species. The reasons for this are intermolecular forces. If one of the species wants to associate more strongly with itself than the other components, then they're going to separate or stay separated into different phases. For example, in this case, the HCl shown is very polar, while the hydrocarbon is not. The polar species have strong dipole-dipole interactions with each other, and these are much stronger than the dispersion forces that it has with the hydrocarbon. Because of this, the ability to form a solution is going to be hindered. Ionic compounds are often able to be part of a solution in a similar way. If a polar compound is introduced to many ionic compounds, they will be able to use their partial charges to surround the ion, stabilizing them. If the substance doesn't have a strong dipole, or the ionic solid is held together so strongly that this won't occur, the species will be considered insoluble in that solvent. Let's look at a simulation of this. Here we have water and ethane. The interactions between the water and the water are very strong because of the hydrogen bonding and dipole-dipole. And those interactions are stronger than that of the water in the ethane. Because of this, the water is going to segregate itself into its own phase, leaving the ethane to its own phase as well. Now let's look at a quick example. Hexane is a common hydrocarbon and is shown here with its 6-carbon chain. Look at the 4 possible options for solutes. Which of these 4 are most likely to be soluble in hexane? Take a moment before moving on. It's of course going to be the other hydrocarbon chain, because the water, or H2O, has hydrogen bonding and dipole-dipole, as does the NH3, and the HCl has dipole-dipole. So because of that, the hydrocarbon is most likely to have the same interactions with the hexane as it does with itself, and will be most likely to allow entropy to let it mix. In review, the physical force behind solution formation is the increase in entropy, or in other words, disorder. If this were the only force, everything would mix. However, intermolecular forces can prevent solutions from forming if the intermolecular forces within one species is stronger than that of the intermolecular forces between the two species together. Or in other words, like dissolves like.